Okay, let's talk about slant asymptotes, and this first sentence here is very important for determining when a function is going to have a slant asymptote, because slant asymptotes only occur when the degree of the numerator is exactly one more than the degree of the denominator. And so if when you're looking for your horizontal asymptote or your end behavior and you notice that the degree is bigger on top, ask yourself if it's bigger on top by exactly 1, because if it is, then the function is going to have a slant asymptote. And a slant asymptote looks very similar to a vertical or horizontal asymptote. And so what I mean by that is that the function gets really close to but does not touch that line, and so it acts like boundary lines for the function. It's just that a slant asymptote is, slanted as opposed to either vertical or horizontal. And so how do we find the slant asymptote? Well, that's why one of the reasons why we learned how to long and synthetic divide back in section 2.4 is so that we could now find the slant asymptote. The good news, though, is that we're going to be able to cut off the work early because we get to disregard the remainder whenever looking for the slant asymptote. So here on letter A, we have a function that the degree in the numerator is exactly 1 more than the degree of the denominator. Notice that we have a x squared term here and an x term here, and so therefore we are going to be allowed to find a slant asymptote. Now, we get to synthetic divide on this particular problem because we are dividing by a term that is linear, x minus 1. And so what number am I going to synthetic divide by? Well, that would be positive 1. If you look at your denominator, that's the 0 of the denominator, and then list the coefficients of your numerator. Be careful, there is no x term, and so that's why I have that 0 there as a placeholder. Now, I don't care about the remainder, so once I do this first first couple of steps, I'm going to be done. And so there's my last line, and so that represents a slant asymptote of y equals 1x plus 1. Okay, here in letter B, we're not going to be able to synthetic divide since we're dividing by a quadratic. And so I'm going to have to write this out and actually long divide here. And be careful, notice that there is no x squared term in that numerator, so we're going to want to put a placeholder of 0x squared there. And so now we're ready to start synthetic dividing. So 3x cubed divided by x squared is going to be 3x, and so I'm going to put that down here above my other x term. Go ahead and multiply 3x by x squared minus 5x plus 1, and that's going to give us 3x cubed minus 15x squared, and then plus 3x, and then change the signs and combine the terms. So change those signs there, and when we go ahead and add those, we'll cancel. I'll get 15x squared plus 1x, and then drop down the next item, and now divide again. So 15x squared divided by x squared is going to be plus 15, and here's the stopping place because everything else from here on out would be us finding the remainder, but because I don't care about the remainder, I have now finished the work to find the slant asymptote. Y is equal to 3x plus 15. Okay, in letter C, notice that this problem is not bigger on top by exactly 1. In fact, this function has a degree that's actually larger in the denominator. And so what's our end behavior whenever we have a function where the degree is bigger on bottom? Well, that means that we're going to have a horizontal asymptote, and it's going to be y equals 0. So this fits that Bobo category where you have the bigger degree in the denominator on the bottom of the function, and so therefore we have a horizontal asymptote at y equals 0.